having defined the exponential function and having noted that this is an increasing function, it's fairly easy to see that to any possible y value, so any positive number, right? Any positive number can be reached by this function. Say 2. Is 2 reached by this function? Yes, here. So which x gives us the value 2? Well, whatever is down here, right? So this function is invertible. In other words, given any positive number, you can find an x value such that this x value gives you the y value. In fact, graphically, one can just think of this as a mirroring in this line here, x equals y. What you do is, what you get is this function here. It's the logarithmic function. So for any base number a, if this function is f of x equals x to the power a to the power x, you get a corresponding mirrored function here, mirrored in this line here. And this function here is called the logarithmic function. And as I said, if you want to find, given an x value, some y value, what you do is you take this y value from this graph. Take the x here, find a corresponding function value, and see what point is this x achieved at for my function here. Well, that corresponds to this. Okay. So we have this. And you can do that for any base number a. They can even cross each other, the two functions here. It's not so important. But if we now show tangent lines, you can see that this logarithmic function, I mean, clearly the tangent lines here will also be mirrored in this line here. So you automatically get that if you choose, I mean, you can see here that here a is smaller than e, here it's larger than e. It's reflected in these tangent lines, right? It's the tangent line here at the x value 0, y value 1. So here the tangent will be at the x value 1, y value 0, right? You can see that at this point they will be parallel. So you automatically get, without knowing anything more about or using any other property, that the derivative of the logarithmic function at 1 is 1. So another way of defining this more arithmetically is using this equation here. So you want to say that, well, my y, I'll just hide the tangent lines. My y up here should, of some value x, should be that number x, which is equal to a to the power y. Y to the power a is my x. That's what we have here. Y equals log a is what we have here. So that's another, it's an arithmetic way of writing the definition that I've tried to illustrate here. So what does that tell us? Well, it tells us that if we take this identity we have here and plug in on this side, then we have that y equals log a of a to the power y, right? In other words, log a of a to the power y is always equal to y. This means that the logarithmic function is the inverse of the power function, and it also holds the other way around, at least as long as x is positive. x should be positive because otherwise the logarithmic function is not defined. Log a of x to the power a, or a to the power log a of x is what's written, equals x. Why is that? Well, just take this side of the function over here, right? And put to the power a, then it says a to the power y, and a of log a to the power x. But a to the power y is a to the power y here, right? It should also be equal to x. And what we have here is a to the log ax is what we have here. So x is equal to this. So this is telling us that you can invert in both orders. First you can use the logarithm, then the exponential function, or you could use first the exponential function and then the logarithm.